Alright, I would like to go over an example from section 3.2. And section 3.2 goes over standard deviation and also other measures of dispersion, but I'm going over an example of standard deviation. And this example I picked out is sample standard deviation. As you can see, it's asking for sample standard deviation. So you know that if we're trying to find the sample standard deviation, the data that's given down here is just a sample. It's a subset of your population. It's not every single value from the population. So since we're determining the sample standard deviation, that is why we're asked to solve for lowercase s, opposed to population standard deviation, which I'll get to in a moment. So we're going to solve for lowercase s, and it mentions this in your textbook that standard deviation, sample standard deviation, is equal to the square root of the summation. Now the notation can get really tricky with the summation notation, so I'll show you what this means in a second. Of each of our x values minus our sample mean squared. And that's divided by the sample size minus 1. So this is a major difference between population standard deviation and sample standard deviation, is the minus 1. So they're not even equivalent to each other, the equations. It's not just notation difference like sample mean versus population mean, where they're exactly the same equations, just different notation. We have this minus 1, so we'll actually get a different solution if this was a population standard deviation. So let's go ahead and just keep that in mind, and keep in mind the notations and the differences. And so what this means, order of operation can get really tricky with this. So I'll show you what this means longhand without the summation notation. This means we're going to sum up each of our values minus the sample means squared. So we're going to take the square of the difference of each value and the sample mean. We're going to sum them all up. I'm not sure if you can hear this, but my baby's crying in the background. That's okay. Not going to faze me. Okay, so take the square root of that entire thing. Let's get it all the way across there. So as you can see, each of our n values from our sample are included here. So dot dot means everything in between. So. Okay, and we are going to divide by n minus 1 still. So with our example, we are going to take the square root, show you what this means longhand. So this is going to be 8, because that's our first value. That's like x sub 1. It's our first value in our sample. And we're going to subtract by x bar. We don't know what x bar is at this point. So I'm going to go ahead and calculate that really quickly. Add them all up, and how many values are there? There's 5, 6, 7, 8, 9, 10 values. So the sample mean, x bar, so I'll just write this up here, x bar is equal to 30.2. So we're going to subtract 30.2 and square that. And we're going to do the same thing with 57 minus 30.2. And we're going to square that. And just for time, I'm not going to do this all out. But we would have 10 of these differences squared. And we're going to have 10 things added up together. Because there's 10 different values, we have to do that with all n values. So we would keep going. And you can go ahead and do this. And it's really important to do order of operation. So I'm just going to give you a heads up of what I would do instead of wasting my time and doing all 10 of these. I'm just going to show you what the order would be of, so wait, n minus 1 would be 9. 10 minus 1. And so keep in mind that the square root also includes the 9. So this entire fraction here is under the square root. So I would do 8 minus 30.2. Then I would square it. So that's 492. 0.84. That's just this first part right here. So just to kind of emphasize what we just did here. This portion right here is this value right here. And then similarly, we would have 57 minus 30.2 squared. $30.2 squared. So that would be 718.24. Okay. And you continue to do this and you'll have 10 things added up here. Now keep in mind that order of operation, we would want to add up all these values before we divide. Okay, and then we would want to take the square root. All right, so just keep that in mind. And I'll tell you what the solution would be of this problem here. And I'll do that really quickly. I'm actually going to use technology just to get the answer really quickly. And again, at the end of each of the sections, so at the end of section 3.1, after the exercises, it will tell you how to do step-by-step instructions of how to do each of these problems with technology using your calculator or like a TI calculator, graphing calculator, or StatCrunch. But anyways, I'm going to put these values in here. And all right, so you should obtain the sample standard deviation to be, let's change colors back to black, to be 14 approximately, let's change that to approximately 14.76. You may get something slightly different due to rounding error, but anyways, that would be the sample standard deviation. Now let's quickly talk about the population standard deviation. So let's imagine that this was not a sample. Let's imagine that these values right here are part of a population. So these are all the values, the entire census. Now, if we wanted to find the standard deviation, we would have to find the population standard deviation of these 10 values, and that would be given by this Greek letter sigma. Excuse me. And so sigma would be equivalent to, now you'll notice that it's quite similar to sample standard deviation. We still have the summation of x sub I minus the mean. In this case, we don't have sample mean, but we have population mean. So that's why I have mu, the Greek letter mu, divided by uppercase n, because we have a population size, not a sample size. But notice that I'm not including the minus 1. So there's the big difference here. So I'll just write that in, let's make that green. So notice that there's a huge difference between sample and population. And it's that minus 1 right there. So keep that in mind, that if you're solving for a population standard deviation, you would use this equation and only divide by n. Okay, so you would use this equation. It would look very similar to before, and I'm just going to write out the answer. And we would get the same exact answer if we were dividing by uppercase n minus 1, but we're not. And so you actually obtain 13.999, pretty much 14 exact, approximately. So okay, so you notice that, and it makes sense that whenever you're solving for population standard deviation and sample standard deviation, and you're given the same values, and you're given, so like in this example, your population standard deviation is always going to be smaller than your sample standard deviation because of that minus 1. You're dividing by a larger number on the denominator, which makes this smaller. Okay, so anyways, it's just the differences between sample, a standard deviation. So again, this is a sample, S as in sample, and sigma as in population standard deviation. And notice also that mean involves x with the sample, and s when you're dealing with a standard deviation. Whenever you're dealing with a sample, you're given like English letters, x and s. And you'll notice that if you're dealing with population parameters opposed to sample statistics, population parameters are dealing with Greek letters like sigma for population standard deviation, and mu for sample or population mean. Okay, so just a quick example of standard deviation.